Hello, my name is Joachim Pieprek, and I would like to talk about a recent development in our field, which is the connection of numerical simulation and machine learning. And I would like to approach this issue from a physics point of view and especially look at the question how to bridge the gap between theory and reality. What do I mean by that? Theory and reality can be connected in different ways by computation. On one hand, we have numerical simulation that starts with a theory with mathematical formulas and deducts practical results out of this. The inductive method of machine learning goes the other way. It starts by collecting data in the real world and then performs some kind of analysis to improve our understanding. But things are not as simple as they look, of course. Both approaches have a number of uncertainties. In numerical simulation, for instance, we can have picked inaccurate models or unrealistic parameters. So typically we end up in a virtual reality that could be quite different from the real world. So there's a clear gap here. On the other side, the inductive method collects data and performs kind of a statistical analysis. And that also leaves a gap because we still need our own intelligence to make sense of this statistical analysis. So there's no automatic improvement of our theoretical understanding. And one of the main problems with this approach is data collection. Since data are sometimes hard to find in the real world, researchers have started to generate these data by numerical simulation. This approach has certainly many advantages, but it also ignores the gap to the real world. Simulation models always simplify reality. And we find examples in material science and in photonics. In material science, people look for new materials this way, and we have many publications on this. And in photonics, people try to optimize the design of photonic devices. And one of the most popular ideas here is inverse design, in which we start with the output, the desired output of a device, and then work backwards in the machine learning algorithm to come up with a design that delivers this output. And here I show these famous examples from Stanford University. With optoelectronic devices, things are a little bit more complicated because now we have to combine optical models with electronic models and thermal models in a self-consistent way. And these models are often approximations, so we have to validate these approximations for each specific case. And we also deal with a number of uncertain material parameters. And in this example of a laser design simulation, the authors have used an artificial neural network to connect a set of input parameters with a set of output parameters. And these output parameters are simply the laser power over the injected current that constitutes a typical laser characteristic, which is calculated in this model. But when we look at the input parameters that they have chosen here, we can see these input parameters are numbers, variables of their theoretical model in many cases. These are not parameters that we use to design a laser diode from scratch. For that we need layer thicknesses, materials, doping, and things like that. So the authors from the get-go are kind of trapped in the virtual reality of their own model. And here are some other examples dealing with the design optimization of gallium nitride-based light-emitting diodes. And these groups try to optimize the design of the LED to achieve a maximum energy efficiency. And both groups do this by machine learning, by different ways of machine learning. And I tried to reproduce these results using the APSYS software, which was actually also used by one of the groups. And I start with the default design here given as a red line, the energy band gap over the vertical axis, and then apply the same design strategies that was published in these papers. And surprisingly, both groups end up with very different design proposals for the same purpose, for maximizing the efficiency. And I simulated the performance for the proposed design optimization, and I only got a little bit of improvement in the case of the Korean group, and in the case of the British group, I didn't get any improvement from any of these design optimization ideas. In all cases, the efficiency was lower than with the initial design at the target current density. But I want to say a little bit more about the Korean example here, because after doing this design optimization, I also played with some of the input parameters, which are often material parameters, and in particular the hole mobility is shown here to have a large influence on the efficiency. But the hole mobility was not even mentioned in the paper, and no values for any other material parameter was given. So this example shows that the uncertainty of material parameters is often larger than the design optimization result that was achieved. And I also want to point out something else. This group came up with the design idea of introducing a thin layer with a large band gap to block electron leakage from the quantum wells. This is a good idea, but this layer is only 1 nanometer thin in their final design, which means that electron tunneling will have a strong influence on the performance of this device. But electron tunneling was not even considered in their model. So that is a clear example that the authors or the result of the machine learning optimization oversteps the limit, the validity limit of the underlying model. So in summary, from these few examples, we can say that authors often don't study the device physics well enough to have a clear understanding what kind of bottleneck process they try to change in their design optimization. They sometimes miss relevant physical effects. They don't validate the simulation model and material parameters by experiment. They use a set of design parameters that is only good for their own model, that is not representative for general design optimization, and they don't explore the design space well enough. So I don't have time to give you more details about the story, but it is already uploaded to the new IEEE preprint server at techarchive.org, and there you can read more about this study. So what can we do about all these problems? The answer is actually pretty simple. Include experimental data wherever we can. So, and there are many ways of doing this. We actually, in industry, these data are collected on a routine basis, and we should start analyzing variations and correlations among these data, for instance, between performance, growth, and processing parameters. Then establish a best case for simulation model calibration and validation, and also for the establishment of an error range, and use measured parameters in the simulation as far as possible directly. For instance, whenever I can get the SIMS doping profile, the measured doping profile, I plug that into the simulation, because that typically gives more realistic results than the intended doping density of any given layer. And of course, when we have simulation results and optimization results, then we should always validate these results experimentally. And one concept that intrigued me quite a bit is the concept of a generative adversarial network, which is used mainly in imaging, and it is able to create real-looking images of people who don't exist. And the way they do this, they use one network that creates a new image proposal, and then another network that validates this image as real or unreal. And we could now do something similar, for instance, using one network based on simulations and another network based on experiments, and try to let them work that out. Why not? It's just an idea. So simply speaking, we have to add experimental data at all levels of our computational analysis, so on the simulation side as well as on the machine learning side, so that we can achieve an interactive and synergetic combination of theory, computation, and experiments. And there are a number of examples in the literature for that. It's not a new idea, of course. Here I found an impressive example from process simulation. We all know that not everything that could be simulated should be simulated, because we know the models are often too simple to represent reality. So in that case, it is better to use experimental data, and they have used etching measurements and plugged these measurements into a process simulation software, so to have better etching results in their simulation. So here's another example from our own work. As you know, gain and absorption are at the center of optoelectronic devices, and it is quite tricky to predict the gain and absorption over a wider wavelength spectrum, as it was necessary in this example of a wavelength converter that includes a photodetector and a laser diode. So what we demonstrated at that time was the inclusion of a high-end gain model that runs on supercomputers and couldn't be directly included in a device simulation. That model was calibrated by comparison to photoluminescence measurements and then parameterized. So we included tables of gain versus wavelengths, carrier density, and temperature into the device simulation. And I think something similar would be a good target for machine learning today. And another example is shown here, where we try to calibrate a laser simulation to a whole bunch of measurements that were available at that time. And it's important in these measurements that we vary certain key parameters, for instance, the laser length here. And we actually saw that even for the same laser length, we got different performance results, which may be related to performance or to process variation. So that would have to be analyzed. And we also had measurements at different temperatures. And it was quite time consuming, took several weeks to calibrate our model in a way that it simultaneously reproduces all these results with one simulation setting. So, and something like this could now be done also by machine learning, I think. So in summary, we can say machine learning application to optoelectronic device design is extremely challenging due to the complex device physics. Simulation-based machine learning often ignores the gap between theory and reality. Bridging this gap requires the inclusion of experimental data. And I would like to close with a famous quote from Albert Einstein: "In theory, theory and practice are the same. In practice, they are not." Thank you very much for your attention.